want to talk about mutations. So mutations are any change or error in a DNA sequence. And these changes can be helpful, they can be harmful, or they can just be, neither, which would be neutral. There's some things I want to talk about that cause mutations. We've got mutagens and carcinogens. Mutagens is a mutation-causing agent, something like a virus or chemicals or radiation is something that causes the mutation. A carcinogen is a cancer-causing agent or an agent that causes cancer. And the more mutations you have, the higher chance of a cancer. All of these mutations can cause cancer, but not all carcinogens are genetic mutations. So there's some overlap there. But I will talk about non-lethal mutations. This is where the bulk of today's lesson is going to be, is over here on this side. We've got non-lethal mutations. So we're going to start with a OG DNA. This is the original DNA. We could do this with a longer strand. We could do this with 20 or 30 codons here. But we're trying to do it with these two, and hopefully you'll be able to see where the difference is. So here's the DNA, AGA, CTC, and the RNA is going to be, the transcription of that DNA is going to be an RNA, and that RNA gets you SER and GLU. You can look right here, and this is a codon chart, or where we can use the RNA to figure out what amino acid there is, a codon wheel. And we can see UCU is going to be U, and then C, and then U. That's going to be SER. Sorry, I think I switched. I moved the screen around. That's going to be SER and GLU. So we see that this DNA, the transcription of that into RNA is going to be this, which will give us this amino acid, which again, that is the central dogma, that DNA transcribes into RNA, and that translates into an amino acid which builds protein. So there's two groups. We got a point source and a frame shift. A point source, I like to think of this almost like you're playing Jenga, and you've got one little block that you can very quickly, and I don't think anybody can actually do this, but this is how I'm picturing it in my head. If you take out one block very, very quickly and replace it with another, then nothing else changes except for the one block you moved. Nothing else moves up and down, nothing falls down, but just that one block. Or if you've seen cartoons where the monster is sleeping or the bear is sleeping or something, and it's cuddling up to like a teddy bear or a toy or something like that, and the person that's trying to sneak away or do something sneaky, they replace that toy with like a rock or a stick or something of similar size and weight. That is a single thing, that they're one point that they're changing, and nothing else changes. And that's what we've got here. This is a point source mutation. It affects one base, and the one that we're going to talk about, the only one that we talk about here, is substitution. So point source and substitution, you can see those as the same thing. It is one point that is changing. So for example, we had AGA up here, and now we have ATA. What you can see is this T replaced this G. Nothing else around it. The A, C, T, C, none of those change. It's just that T in the DNA. And if something changes in the DNA, it will change in the RNA all the time. It will always change in the RNA. So we've got ATA is transcribed into UAU, and that's going to be different than what we had up here. This is UCU. And so therefore, where UCU, UCU got us SER, UAU, UAU is going to get us TYR. So we see that amino acid TYR is coming from the UAU. But we still have the GLU. So you see the proteins that are, or the amino acids that are made are the same on the right side. They're not the same on the left side. So this mutation changed what amino acid was there. And this could maybe change somebody's eye color, or could give them some kind of beneficial adaptation for what they're doing, camouflage, or maybe it leads to them having high risk for disease. It can be a bunch of different things, but this is a point source change mutation, and is substitution. Then we get to these two, deletion and insertion. They're both examples of frame shift. Frame shift. And so a frame shift affects every base that follows, whereas point source only affects this one letter. A frame shift affects all of the letters after that. An example of, or an analogy for frame shift, maybe you're running in a race and you are in third place the entire time, and the person behind you is in fourth place, the person behind them is in fifth place, and all of a sudden somebody jumps into the race that has not been there at all, and they win the race. Forget about the rules or why they should be able to do that, but somebody jumps in front of you, which you're in third place, so somebody jumps right in front of you and they take third place. Well, first and second place are not affected, but every place after the person who cut in line, everybody else is going to be one behind. Or in that case, the opposite of that would be if you were to just, if you were in third place the entire time, and right at the end you just started walking or disappeared, got in a car and just drove off. Now you're no longer in third place, you're out of it, and now fourth place is now third place, and fifth place is fourth place, and so on and so forth. Everybody after you is affected. And that's what we have here. With deletion, you can see this AGC, the A that was here in the original DNA, in this DNA, the A is deleted. So that shifts everything forward. And you'll notice we've got a full codon here, 3, but right here we have 2. And when it replicates this error, it replicates this mutation, and it makes something different now. So instead of making SER and GLU, now it's going to make SER and nothing, because there's only two base pairs here, nitrogenous bases. And so that's it. That's what we've got. So now we only have one amino acid made. If there was a line of 30 codons, 30 groups of these 3s, then it would mess up every single one after them, very possibly every single one. I also want to point out that up here, AGA, UCU would be the RNA. UCU made SER, and UCG, this one happened to have all of them made SER. So just because all of them, just because it's a different last letter or two does not mean that it's completely different amino acid. It could be a different codon, but the same amino acid. You just have to tell. So there's SER over here. Here's also SER over here on this side. So you just have to kind of see if it's going to make any substantial change in the amino acid. So that's deletion. You delete one. If you insert one, here we inserted T right here instead of saying AGA. Now it's AGT, and then it picks up ACT. Everything after that, this insertion is off one. And you can kind of tell if there's only one codon or one nitrogen base added or deleted, you can tell, because one that's inserted, it'll be an extra one off here by the side, and one that's deleted, there'll be an extra 2 because there was 3 here and they lost one. So that can give you a little hint, but you need to make sure that you can see where the nitrogen base was added or taken away or substituted. So sometimes there is what we call a silent mutation, and this can describe something that does not affect the protein that is made. And we see that here with AGT and CTC. If you replaced what was a U in the RNA with a, this would be the RNA version of this. I didn't write the RNA on here. The RNA version would be UCA, and that would still get you SER. So just like we talked about a second ago, just because it changes something, if it changes in the DNA, it will always change it in the RNA. If it changes it in the DNA and the RNA, it might change it in the protein that's made, in the amino acid that is selected for. It may not. And in that case, it's going to be a silent mutation. It's not going to affect which protein. There is a mutation there, but it's not going to affect the protein that is being made, the amino acid that is being made. So we'll continue on with that in mind. So when we talk about mutations in your body cells, if you are born and you have a mutation in your body, let's say at age 2 or 3 or 4 or 20 or 30, and you have a mutation in your body cells, that is not going to be transferred in a body cell, is not going to be transferred to your offspring. So if you're a male, your sperm, or a female, your egg is not going to contain that because it's in a body cell. If that's where the mutation happens. If the mutation happens in your sex cells, in your gametes or germ cells or sperm and egg cells, then that is inheritable, and that means that it can be passed on to your offspring. This is obviously a beautiful baby down here. And so body cell mutations are not passed on. Sex cell mutations are passed on. And that sex cell mutation, if it happens in you and you have have offspring, then that offspring and all of their cells, that they will have that mutation. Because remember, that one cell that we start off with, that zygote, upon fertilization, every cell comes from that cell. So if there's a mutation in those cells, then it will spread to all their cells, which may be, again, it may be helpful, it may be harmful, or it may just be neutral. Could be neutral. So I said a word there, inheritable. Inheritable is something that you get from your parents. So you may have heard somebody say that you look just like your aunt or your grandpa and you look just the same or something like that. That is inheritable. You inherited that from your biological parents. Heritable mutations, though, are not gained from your parents. Heritable mutations are going to be occurring after birth. They're not inherited by you. Now, depending on the situation, you could pass them on to the next generation, but they are not inherited from your parents. It's something that happened to you. It can be caused by the environment. So, for example, radiation. You go to the dentist, they probably put a lead vest on you when they take x-rays, and the dental assistant, dental hygienist, or the dentist, they step out of the room when they take an x-ray. And that's because those x-rays can cause damage to your cells. They can increase your mutations. They can, that would be radiation up here at the top, the mutagen. So what they do is they're minimizing their risk to doing that because they do that all day. They may do a dozen in a day, and over time that can be very harmful if they're exposed to it. So they put a lead jacket over you, and the only thing exposed is, hopefully where the x-ray is going in. But so that's an example of radiation causing it. Or that could be the sun causing it. That we got chemicals, processed food, burnt food. These are things that can be caused by the environment, changes in the environment. Or sometimes there are chemicals put into your water. So if you put your water in a glass container versus a plastic container and let them sit in the sun, there's chemicals from the plastic that are possibly in your water, and then you're consuming them. And so these can cause problems in your body. And cancer, we've all heard of cancer and probably maybe experienced somebody being harmed or their body being eaten away by cancer. But cancer is uncontrolled cell division. And what that means is that one of the cells that should have gone through apoptosis, which is voluntary cell death, when there's a problem, instead of them going through apoptosis and dying, the cell the cell continues dividing and going through division. Well, eventually, going through division very rapidly, very quickly, there's a lot of cells growing. That will grow what you've probably heard of, a tumor. And this can be treated by chemotherapy, but if you'll think about it, if rapid cell division is what cancer is, and chemotherapy is attacking that, the chemotherapy oftentimes is looking for cells that rapidly divide. And so other healthy cells in your body that are also described that way could be attacked, things like your hair. So if you have chemotherapy or radiation, that sometimes you may have had somebody go through those and then they lose their hair. And that's because hair cells go through rapid cell division, not uncontrolled, but they go through rapid cell division, and the medicine attacks them similarly to the way that it attacks cancer.